A very good evening to all my lovely students. Welcome back to your YouTube channel, Shri Chatelier Goshala. Today, I am Anirudh Mehta. I'll be talking about a very important topic from NEET point of view, which is Chatelier principle from the chemical equilibrium topic. Okay. From the theoretical point of view, this topic is the most important topic from your chemical equilibrium chapter. Every year, one question has to come from Chatelier principle, and this particular principle has to be used in many other chapters, like in organic chemistry also we use it, and in other chapters also we'll have to use the Chatelier principle. What is it? Let us write about it. Chatelier principle is nothing but it is an anti-Gandhi principle. Okay, as Gandhiji told us that if someone slaps you on your right cheek, you show your left cheek to the person. You follow the non-cooperation movement and all, but the Chatelier principle is a anti-Gandhi principle. What does it do? Whatever stress you will apply to the reaction, whatever stress you will apply to the reaction will apply the stress back to you. Means that you now forget about that and now remember that what is Chatelier principle? Whatever change you will try to do on a reaction which is at equilibrium, reaction will change itself in such a way that the stress applied has to be minimized. Means if you say I will try to increase the reactant, reaction will say I will decrease the reactant. If you say I will try to increase the product, reaction will say you wait, I will try to decrease the product. So what is Chatelier principle? Whenever a reaction is at equilibrium, and any stress is applied on it, then the equilibrium gets disturbed. And in order to re-achieve the equilibrium, reaction shifts in one of the direction, either forward or backward, in order to minimize the applied stress. That is Chatelier principle. We will quickly look at how the questions can be asked from Chatelier principle and what are the stresses you can apply. The very first type of stress that you can apply is going to be concentration change. Effect of concentration change. First thing you need to keep in mind, this is only valid for gaseous reactants products and aqueous solutions. Only valid for gases and aqueous solutions. For solids, as you all know, the active masses of solids and pure liquids is anyways constant. So it is not going to have an effect. Now, how do we look at it? For example, I'll make you imagine this with the help of reaction quotient. I hope all of you have an idea about what is reaction quotient and how do we compare it with the equilibrium constant. If I have a reaction like, let's say, Haber's process I am writing, N2 gas plus 3H2 gas giving you 2NH3 gas. Okay, this reaction is right now at equilibrium. I can write its reaction quotient as concentration of ammonia square by concentration of nitrogen power 1, concentration of hydrogen cube. I hope all of you know how to write the Q and K. This is the Q and K is also this. Now what will happen? Let us see what will happen when I add nitrogen or when I add hydrogen, if I add ammonia. Let us see what will happen to the Q first. As soon as you add some nitrogen, right now the reaction is at equilibrium, so Q and K are actually equal. Okay, before anything has happened, Q and K were equal. Q and K were equal. Okay, reaction was at equilibrium. Now what I did is I started adding some nitrogen. If you add some nitrogen beta, what will happen? See, you have increased the denominator. So what will happen? Q will start decreasing. So as soon as you do this, suddenly what will happen? Reaction will get disturbed and Q would go down. Q has gone down because of addition of nitrogen gas. Now, you have done the disturbance. Due to disturbance, Q goes down. Reaction says you are adding nitrogen. I will try to take out the nitrogen. I will consume all the nitrogen. So, reaction will start moving where? You can see Q has gone down. So, Q always tries to reach to K. So, when Q goes up, reaction moves forward. Reaction starts moving forward to re-achieve the equilibrium. So, what we have to remember now is when I add reactant, reaction says I will remove reactant. How to remove reactant? By sending the reaction forward. I will consume all the reactant. So, when you increase the reactant, where does the reaction go? Forward. Okay, can we remember? Reactant addition, reaction goes forward. So, in the case of H2 also same thing will happen. Hydrogen will add means Q will decrease. So, here also Q will suddenly go down, and as the Q goes down, now reaction is disturbed. Reaction again wants to reach to equilibrium. Q tries to go up, reaction moves forward. So, addition of reactant, reaction goes forward. Addition of product, what will happen? Addition of product. When I add ammonia, if I add ammonia, what is going to happen is, you can see here, if I add ammonia, Q will increase. When ammonia will increase, reaction quotient Q will increase. So, Q will surpass the K. Q will surpass the K. Something like this. Now, equilibrium is disturbed. We know that Q always tries to become equal to K. Q comes down, reaction goes backward. I hope now it is mathematically also clear to you, theoretically clear to you. If I try to increase product, reaction say I will consume product, I will go backward. What will happen if I remove product? If I remove product, reaction will say I will make more product, reaction will go forward. So, removal of ammonia, forward. Removal of ammonia, forward. When I remove ammonia, forward. I hope it is clear to everybody now. When I remove nitrogen or hydrogen, backward. Reaction will say Chatelier will say you are trying to remove nitrogen, hydrogen. I will create even more amount of nitrogen, hydrogen. So, whatever you try to do to the reaction, reaction will do exact reverse to you to re-achieve the equilibrium. Okay, is the first point clear? Concentration. Now, let us see what type of question can be asked from here. Now, it's not that simple to remove this because we can't put our hand inside the reaction vessel and remove nitrogen, hydrogen. There are some reagents which will be used to do this. Like, for example, all of you remember that KOH absorbs CO2. Okay, this is the first point you should know. KOH absorbs CO2. So, if I have reaction CaCO3 solid in equilibrium with CaO solid, CO2 gas. For this reaction, a question can be asked. How can you increase the decomposition of CaCO3? How can you send the reaction forward? They can ask by, so reaction moves forward. Reaction moves forward when, and different options will be given, like when CaCO3 is added, when CaO solid is removed, when CO2 gas is added, or when KOH pellets are added, like this. Now, most of the students do mistake here by thinking that, okay, sir told when reactant is added, reactant increases, reaction will try to move forward to consume it. So, answer should be option 1, and it is absolutely incorrect. Beta, Q does not have the concentration of CaCO3, no. For this particular question, what will be the formula of Q, reaction quotient? It will be concentration of CO2 to the power 1, that's all, because CaO is solid, its active mass is taken as 1. CaCO3 is solid, its active mass is taken as 1. So, when I add CaCO3, nothing happens, Q does not change. Okay, so that's not the answer. CaO solid removed, nothing will happen. If I add CO2 gas, for CO2 Chatelier is valid, So we'll say if I add CO2 gas, I am trying to increase the product, reaction will go backward. So this also can't be the answer. So what KOH will do is KOH will eat the CO2. KOH will eat the CO2. When KOH will absorb or eat the CO2, then KOH is trying to decrease the CO2. Reaction will say I will produce more CO2 and then the reaction will move forward. Okay, this is the effect of concentration. Okay. Second one is the effect of temperature. Effect of temperature. In the exact same way, I'll tell you now. Okay, effect of temperature, it's very easy to learn. Just that whenever you want to know effect of temperature, you must know the enthalpy of reaction, whether the reaction is endothermic or the reaction is exothermic. Okay, if the reaction is endothermic, endothermic reactions are generally decomposition reactions. So I'll show you one reaction which is N2O4 decomposing to give NO2 gas. We should know that N2O4 is colorless gas, whereas NO2 has a red-brown color. It has a red-brown color. Okay, and it is an endothermic reaction, like that they will mention delta H is positive. Now we need to know what is the effect of temperature on such reaction. So I could think of this reaction as endothermic means N2O4 absorbs heat and move forward. Absorbs heat and move forward. So heat is a reactant for us here. Heat is a reactant. If I try to increase temperature, so when I increase the temperature, I am trying to supply heat. I am trying to increase the heat. Okay, I am sending heat to the reaction. Reaction says you will try to increase the heat. I will absorb all the heat or I will consume the heat. So reaction will start moving forward by consuming the heat. Okay, whenever you add reactant, what happens? Reaction moves forward. So temperature increase, reaction moves forward. Give me heat, I will go forward. That is what happens in the endothermic reaction. So as the reaction will move forward, they won't ask reaction moves where, they'll ask what will happen to red color. So we can say red color intensity increases. Reaction moves forward on increasing temperature. Okay, now if you want to understand it mathematically, what happens is when you study the effect of temperature on the equilibrium constant, for endothermic reaction, equilibrium constant increases with the temperature increase. Equilibrium constant increases with the temperature increase. There is one formula behind it. If you want, you can remember that formula by looking at in the NCERT. This formula is present. So when you increase the temperature, for right now you can learn it, K equilibrium also increases. The formula looks like this. It's not required to learn this formula right now. Log K2 by K1 is 2.303, delta H by 2.303 R, 1 by temperature 1 minus 1 by temperature 2. This is the formula which tells you relation between equilibrium constants at two different temperatures. You will see that whenever you increase temperature here, if delta H is positive, then on temperature increase, K will also increase. Okay, so you can just learn this right now and remember that. So what will happen as I increase the temperature? Before the reaction was disturbed, it was at equilibrium. Q and K were equal. Q and K were equal. As soon as I increased the temperature, what happened? K went up. As soon as I increase the temperature, here Q does not change. Here actually with temperature K changes. K went up. Now we know Q is always trying to chase the K. So Q is chasing the K. Q wants to move up, reaction moves forward. Okay, I hope it is clear to you, and this is very easy to check now. So increasing temperature, reaction moves forward. Same way, when I decrease temperature, reaction moves backward. Reaction moves backward. Okay, I hope it is clear to you. In this case, I can say on decreasing the temperature, K will go down. If K goes down, Q tries to chase the K by moving down, reaction moves backward. This is true for the endothermic reaction. So the question can be asked like this. Melting of ice is favored by, okay, low temperature, high temperature, low pressure, okay, or something like both B and C. Something like this. So, melting of ice. Till now I have not told you the effect of pressure. Here actually you can remember it from now on that ice has a very porous structure. Okay, ice has a very porous structure. So that is why ice is low density as compared to water. Ice has low density as compared to water. So I want to send this reaction forward towards high density side. Okay, so ice having a very porous structure, ice has a very large volume. Okay, a lot of air gaps are there. So volume is very large here. Ice has large volume. Volume of water is less. As you increase the pressure, what happens is on increasing pressure, volume will decrease. On increasing the pressure, volume is going to decrease. So on increasing pressure, actually the ice melts. So you can remember that point as well from now on, that two factors are there which help in melting of ice. One is very, very clear that we know melting of ice is endothermic process. This is delta H positive. So just like I just told you, on increasing temperature, reaction will move forward, water will form. So high temperature is one of the option. Other will be high pressure. So whenever you look at any physical equilibria like this, effect of pressure is always there. What is the effect of pressure? Whenever we increase pressure, reaction moves towards higher density side. Okay, you can keep it in your notes and remember this. This is what happens for the endothermic reaction. For exothermic, exact opposite. For exothermic, exact opposite. For exothermic reaction, as temperature increases, equilibrium constant actually decreases. So if you want to know mathematically what happens, I have given you this. If you want to know theoretically what is happening, is for an exothermic reaction, if I take an example of exothermic reaction, okay, we can talk about a reaction like COCl. Let me take the example of an exothermic reaction like Haber process, N2 plus 3H2 giving you 2NH3. Okay, this has a delta H of somewhere around minus 42 kilojoule per mole. Okay, so delta H is given negative here. So they could ask you that what is the condition to improve or increase the yield of ammonia by Haber process. Okay, this could be a question regarding the temperature if they ask you. So now we need to know that Haber process is an exothermic process. So actually heat is a product here. Heat comes out during the reaction. Heat comes out during the reaction. So what will happen if I try to increase temperature? If you increase temperature, you are trying to add the product. You are trying to increase the product. So on increasing temperature, actually reaction will move backward. Reaction will say, you are giving me heat. I will absorb all the heat. I will move backward. So that's not the correct answer here. Increasing high temperature is not a good option for us. High temperature is not a good option for us. Okay. Then low temperature. If I try to decrease the temperature, decreasing the temperature means nothing but taking out the heat. You took this mixture and kept it into refrigerator, let's say. Okay, so what will happen? Refrigerator will suck its heat out. So when the heat is taken out, reaction will say you are trying to decrease the heat. I will make more heat by moving forward. So reaction will move forward, more ammonia will produce. So decreasing temperature becomes a good option for us. So yes, low temperature is the correct answer here. But one thing you should know, it's not like low temperature means you can keep the temperature 0 degrees Celsius or minus 10 degrees Celsius. Not like that. This is about shifting Le-Chatelier principle. There is something else called as activation energy, which is required to do the reaction. So always remember that at low temperature does not mean very low temperature you can keep. Here we keep the temperature somewhere around 700 Kelvin. So 500 degree Celsius around temperature is still required to do the reactions. This is the optimum temperature. It's not very high temperature from industry standard point of view, but this is the optimum temperature we keep around 700 Kelvin. Okay, I hope it is clear to everyone. This is the effect of temperature. Next is the effect of pressure. Effect of pressure. If the reaction is at equilibrium, and I pressurize the reaction, if I increase the total pressure, what will happen? So let me take one example that the reaction is, let's say, I am taking the example of a reaction like PCl5 gas in equilibrium with PCl3 gas plus Cl2 gas. Okay, this is the first reaction I am taking. Then I'll ask you to finally remember the effect of pressure. Now this reaction is at equilibrium right now. Okay, this reaction was at equilibrium. And the total pressure of the system is, let's say, 5 atm. So total pressure is P total, which is 5 atm. Now what I do is, I increase the pressure, I move this piston downward. So here PCl5 was present, PCl3 gas were present, Cl2 gas was present. All these gases were present. Now I increase the pressure from 5 atm. I shift this piston downward and I increase the pressure from 5 atm to, let's say, 10 atm. Now the pressure total is 10 atm. Okay, no problem. Still PCl5 is there, Cl2 is there, PCl3 is there. Now, everyone listen carefully. How can I write its Q? Reaction quotient in the terms of partial pressure, I can say it is partial pressure of PCl3, partial pressure of Cl2 by partial pressure of PCl5. Now what has happened? I increase the total pressure to double. Due to this, what will happen? Due to this, all the partial pressures will also double. Because what is partial pressure? Partial pressure is mole fraction into P total. What is partial pressure? Mole fraction into P total. Now partial pressure is mole fraction into P total. I did not change any mole fraction. Did I add any new PCl5? No. Did I add any Cl2? No. Did I add any PCl3? No. So I did not change any mole fractions. So partial pressure is mole fraction into P total. If I make the P total double, then all partial pressures will also double. So here what has happened is the top part has doubled 2 times, the bottom part has doubled only 1 time. So what will happen? Q will increase. Can I say on the top doubling is happening twice, at the bottom doubling is happening only once. So Q increases. Reaction got disturbed, Q got increased. Okay, again I am just trying to imagine from the equilibrium that initially Q and K were equal. Initially Q and K are equal. As soon as you increase the pressure, I'll show it here. Initially Q and K were equal. As I increase the pressure, on pressure increase, what happened? Q increased. On pressure increased, Q has increased. This is what happened as pressure increases. So what will happen? Q always tries to reach to K, reaction moves backward. Reaction moves backward. Now just learn this, from now on always this will happen. Whenever you increase pressure, reaction runs towards the side where less gaseous moles are present. Less gaseous moles are present. So pressure increase means reaction goes towards less gaseous moles. Here 1 mole gas was there, here 2 moles gas was there. So pressure increase, reaction runs towards less moles of gas. Pressure decrease, it will move forward. I hope it is clear to everybody. Pressure increase, pressure decrease. So just learn it from now on. Just learn this point from the Chatelier principle. Effect of pressure is easy to remember. That on increasing pressure, reaction shifts in direction of lesser gaseous moles. Okay, simple. On decreasing pressure, reaction shifts in direction of higher gaseous moles or more gaseous moles. That is what we need to remember now. So just look at the reaction. If you increase pressure, reaction goes towards lower gas moles, and if you decrease pressure, reaction goes towards higher gaseous moles. Okay, just learn this point. I just told you how to imagine it with Q and K. Okay, now let us see what type of question can come here. They can ask you that which of the following reaction has no effect of pressure change? Which of the following equilibrium has no effect of pressure change? They can give you reaction like Haber process, N2 plus 3H2 2 ammonia, all are gases. Decomposition of limestone, decomposition of HI gas, or decomposition of N2O4 gas. Okay, so such a question if it comes, then I hope you are able to tell the answer yourself. What is the answer? What is the answer? I will wait for you to tell the answer in the chat box. Okay, in the comment box you can tell the answer. The answer is very good. It is option C. Here left hand side are also 2 gaseous moles. Right hand side are also 2 gaseous moles. So we say delta Ng for such reactions is 0. So remember it, whenever delta Ng is 0, in any chemical equilibrium, then there is no effect of pressure, because now the Q will increase at the top and bottom equally. Here also it will double up on the numerator, it will double up at the denominator also. So Q will not change. With the pressure, if I increase pressure, reaction goes towards lower moles. But where is the lower moles? Both sides are equal moles only. No? Reaction will neither go forward nor backward on increase of pressure as well as on decrease of pressure. Okay, this is the type of question we can get. Now another question where you generally do mistake is, they can say, for which of the following reaction on increase in pressure, equilibrium constant increases? So remember it, that equilibrium constant is independent of pressure. Okay beta, whenever you change pressure, actually Q changes, not K. Equilibrium constant will only change with one thing, which is temperature. So effect of concentration, what changes? Q changes. Effect of temperature, what changes? K changes. Endo के लिए K increases, for exothermic reaction K decreases with temperature. With pressure also what changes? Only Q changes. Whatever is the effect of pressure, exact opposite is the effect of volume. Can you see here? When I increase the pressure, what actually I have done is I have decreased the volume of the gases. Gases were kept in a bigger volume before, now the volume is decreased. So now I'll just ask you to learn the direct relation with the volume as well, which is fourth one, effect of volume. As we know, PV equal to nRT, pressure is inversely proportional to volume. So whatever is the pressure effect, exactly opposite is the volume effect. That is, as volume increases, pressure decreases. When pressure decreases, reaction goes towards higher moles. Reaction goes towards higher gas moles side. Okay, so volume increase same as pressure decrease. Volume decrease same as pressure increase. Reaction goes in the direction of less gaseous moles. Okay, beta. I hope it is clear to everyone. This is about the fourth factor. So, effect of volume is just reverse of effect of pressure. They can ask you that on shifting the equilibrium mixture to a larger volume container, reaction shifts backward in which of the following equilibrium? Like that they can ask, and they have given the equilibrium like SO2 gas plus Cl2 gas going to SO2 Cl2 gas, PCl5 gas going to PCl3 gas plus Cl2 gas. Okay, like this they have given you the option, and one more option I am writing here is N2 gas plus O2 gas giving 2NO gas. Okay, and these both A and C. Let's say something like questions like this options are there. Okay, so in this case, what is the question? See carefully. If I shift the reaction to the larger volume container, what will happen? It is the pressure decrease case. Volume will increase, pressure will decrease, and we know whenever pressure decreases, reaction go towards more gaseous moles. So this reaction will go towards more gas. Left hand side are 2 gas moles, right hand side are 1. So reaction will move backward. So this is one of the answer for us. A has to be chosen. Reaction will move towards more gaseous moles backward. In the next one, right hand side has more gaseous moles, so it will move forward. So that is not our answer. Next one, left hand side are also 2 gases, right hand side are also 2 gases. Reaction stays at equilibrium, not our answer. So only A option we have to choose. Okay, I hope it is clear to everyone how to check the effect of volume. And the final last one before I end the class today, we'll see the effect of addition of inert gas. There are 2 ways you can add the inert gas. One at constant volume, one at constant pressure. Here I'll take the help of simple PV equal to nRT equation. Okay, PV equal to nRT equation I will use here. So let's say I have a reaction at equilibrium right now, and the reaction is in a closed vessel without any movable piston. Reaction has nitrogen gas, reaction has hydrogen gas, reaction has ammonia gas. They are all at equilibrium, N2 plus 3H2 giving you 2NH3. This equilibrium is there. Okay. Now let's say total pressure of the system, P total, is 5 atm. Okay, just randomly I am taking one number. Now what I did is I introduce some amount of helium gas into it. I introduce some amount of helium gas into it. I introduce some amount of helium gas into it, keeping the volume constant. Means I am not letting the chamber to become larger or anything. It's a fixed volume container. I introduce some helium gas. What will happen now? If I introduce some helium gas, some helium comes inside. If I add some helium gas, beta, you tell me, will it change the moles of nitrogen, hydrogen or ammonia? Answer is no. It has not changed the moles of nitrogen, hydrogen and ammonia. So what is the formula of pressure? So pressure into volume is equal to nRT. PV is equal to nRT. So I can say pressure of nitrogen will be moles of nitrogen RT by volume. Now, did I change the moles of nitrogen? Answer is no. Did I change R? Answer is no. Did I change temperature? No. Did I change the volume? No. So when I do not change the volume, bache, whatever you add inside it, whatever inert gas you add, partial pressures of these gases will not change. Okay? Partial pressure of nitrogen is moles of nitrogen RT by volume where the nitrogen is sitting. Now the nitrogen is sitting in this volume. I am not changing the volume. So pressure of nitrogen is nRT by V. I did not change moles. R and T are also constant. I did not change volume. So pressure of nitrogen, pressure of hydrogen, pressure of ammonia do not change. Okay, so remember it now. In a constant volume flask, these partial pressures do not change. Although total pressure will increase, obviously. Okay, initial pressure because of these three people was 5, helium will bring its own pressure, let's say 2 atm it brought. So total pressure has become 7 atm. P total has become 7 atm, but I could not change the partial pressure of each individual reacting gas. So Q will remain constant, it will have no effect on equilibrium. Okay, so this is not, don't think of it as pressure increase case. Here pressure increased not due to our forceful, compression. We did not increase the pressure like that. We added some extra moles of gas coming from outside like helium. That increased the pressure, but it did not change our partial pressure of reacting gases. So Q is still undisturbed, reaction is still undisturbed, it is still at equilibrium. Alright, very good. Now, next is, if I add at constant pressure, if I add inert gas at constant pressure, now I have taken reaction mixture, but this time I have taken it in a vessel with movable piston. Here nitrogen was there, hydrogen was there, ammonia was there. These three gases are right now at equilibrium. Okay, right now at equilibrium. Right now pressure P total is 5 atm. P total is 5 atm. I am saying that I want to keep the pressure constant. The pressure must remain 5 atm. So what will happen? If I add some helium, if I introduce some helium into it, when helium also enters inside, new moles are entering inside. New moles are entering inside. Okay. In order to keep the pressure constant, here volume has to increase because PV equal to nRT. So pressure equal to nRT by volume. Pressure equal to nRT by volume. If I keep the volume this side only, pressure into volume equal to nRT. What did I do? I just introduced extra moles. I increased the number of moles by adding some helium. But I am saying that pressure is constant. Pressure is constant. I can't change the pressure. So what will happen? Volume has to increase. So when you increase the right hand side, obviously at the left hand side also has to increase, but pressure I'm not changing. So volume has to increase. So what will happen, as soon as helium will enter here, this room will expand. As soon as expansion occurs, now can I say it is a case of volume increase only? As soon as the volume will increase, as volume increases, partial pressure of nitrogen, partial pressure of hydrogen, partial pressure of ammonia, all their pressures will start decreasing. So now equilibrium will get disturbed as soon as you entered helium. So beta, if you enter helium at constant volume, pressure total increases, but their partial pressure were not changed. Okay, when you add extra moles of helium, total pressure increases, but their partial pressures did not change because they were in the same volume. I did not add any extra moles of nitrogen, hydrogen, so their partial pressures were constant. But here, when I add at constant pressure, volume will increase. As volume will increase, moles of nitrogen, hydrogen, ammonia are same only. When volume will increase, their partial pressure will start decreasing. So it's a case of partial pressure decrease. So pressure decrease case or volume increase case, same as that. So it is same effect as in case of decrease of pressure or increase of volume. Which was what? When the pressure is decreased, reaction goes in direction of greater gaseous moles or higher gaseous moles. So here also reaction will start moving in the direction of higher gaseous moles. Okay, so like this you can study the Lee-Chatelier principle. I hope it is clear to all of you. That is all from my side from today, and keep learning. All the best for your NEET 2025. Thank you.